Toyota spent 15 years telling you the battery wasn't ready. They were right, theirs wasn't. CATL just shipped a battery that goes 1,500 kilometers on a single charge, recharges in under 7 minutes, and weighs less than what BMW puts in a sedan today. This isn't a prototype, it isn't a concept car announcement. It's already in production vehicles right now. The last credible argument for buying a gas car didn't fade out slowly. It was deleted in a single product launch. To fully appreciate what CATL has accomplished, you need to understand what was actually happening behind closed doors in the automotive industry over the last decade. The giants of traditional manufacturing, Toyota, Volkswagen, BMW, collectively represent over a century of engineering heritage and trillions of dollars in industrial infrastructure. When battery electric technology began its serious rise around 2013, these companies faced an uncomfortable choice: adapt aggressively, or buy time. They chose time. Their strategy was not to discredit EVs directly. That would have been too transparent. Instead, they chose a subtler weapon: doubt. Range anxiety became the industry's most durable talking point, not because it reflected a permanent engineering ceiling, but because it reflected technology at one specific frozen moment, amplified for maximum psychological effect. Consumers read about drivers stranded on highways, unreliable rural charging, battery degradation. They absorb story after story until those limits began to feel permanent, rather than transitional. Toyota was perhaps the most committed to this posture. For years, its senior leadership publicly questioned whether pure battery electric vehicles would ever be practical for mainstream buyers. The company doubled down on hybrids, promoted hydrogen fuel cells as the more rational path, and consistently pointed to solid-state batteries as the real answer, always just a few years away. That timeline shifted from 2025 to 2027 to 2028, with predictable, deliberate frequency. What these companies failed to account for was a parallel universe of engineering happening simultaneously in Shenzhen, China. CATL, Contemporary Amperex Technology Company Limited, is a name most consumers in North America and Europe would not recognize, but ask any automotive engineer or product director on the planet, and they know exactly who CATL is. Founded in 2011, the company grew to become the largest battery manufacturer on Earth, controlling approximately 37% of global market share. Their cells power Tesla, Mercedes, Benz, BMW, Volkswagen, and virtually every major EV brand worldwide. For most of its history, CATL's role was supplier. They manufactured the chemistry that enabled other people's visions. In 2025, that changed. CATL deployed their most advanced architecture directly into production vehicles under their own technology banner. The product is called the condensed matter battery, and it does not represent incremental progress. It represents a generational discontinuity. Production integrated system capable of delivering 1,500 kilometers of real-world range on a single charge. The companies that spent a decade telling you the battery wasn't ready are now scrambling to respond to one they cannot currently match. To understand why 1,500 kilometers is such a dramatic number, you need to understand the trap that EV engineers have been stuck inside for years. The mass spiral, the relationship between range and weight in battery. Electric vehicles is recursive in the worst possible way. More range requires more energy requires more cells mean more mass. A heavier vehicle consumes more energy per kilometer just to overcome its own inertia, which means you need even more cells, which adds more weight, which increases consumption further. The cycle compounds, and escaping it through conventional chemistry is essentially impossible beyond a certain threshold. If you attempted to engineer a 1,500-kilometer vehicle using standard lithium iron phosphate chemistry, found in most mainstream EVs today, the required battery pack would be so large and heavy that the vehicle would become physically compromised. Suspension geometry would operate outside designed load parameters. Tire ratings would be exceeded. Aerodynamic efficiency that underpins the range calculation would be destroyed by poor weight distribution. You would technically have 1,500 kilometers of stored energy. But the car itself would consume that energy at an accelerated rate, collapsing the real-world number dramatically. Today's best European flagships, the Mercedes EQS, BMW i7, Porsche Taycan, achieve energy density figures around 260 watt-hours per kilogram. Years of serious refinement. Real investment. Under real-world conditions, they deliver between 500 and 620 kilometers before recharging. Impressive, but insufficient to eliminate the final argument legacy automakers kept in reserve: the long road trip, the cross-country drive, the journey where stopping to charge is a genuine inconvenience rather than a brief pause. Thermal management compounds everything. High-density energy storage generates significant heat during rapid discharge and fast charging. Managing that heat traditionally required thick extruded aluminum casings, heavy reliable, and adding hundreds of kilograms of dead weight that contributed nothing to energy storage, only worsening the mass spiral they existed to protect against. CATL did not solve the problems within this architecture. They discarded the architecture entirely. Condensed matter battery starts at the molecular level, with the most critical and limiting component in any lithium-ion cell, the electrolyte. In every conventional cell, the electrolyte is a liquid, a conductive solution that ferries lithium ions between anode and cathode during charge and discharge cycles. Liquid electrolytes carry two structural weaknesses at high performance levels. First, they become thermally unstable under aggressive cycling, the root cause of thermal runaway, and the battery fires that generated alarming headlines throughout the 2010s. Second, their physical chemistry imposes a hard ceiling on energy density before volatility becomes dangerous. CATL replaces this liquid with a biomimetic condensed-state electrolyte, a semi-solid material engineered at the micron scale to replicate the ion transport mechanisms found in biological cell membranes. Living organisms have evolved extraordinarily efficient systems for moving ions across membranes with speed and structural precision. CATL's materials team translated that biological principle into an industrial electrolyte that moves lithium ions as efficiently as liquid without its thermal instability. With chemistry stabilized at this fundamental level, CATL pushed energy density to 350 Watt-hours per kilogram in production-grade implementations. That is approximately 35% higher than the best conventional cells in current European vehicles, and nearly double standard LFP energy density. In practical terms, the same battery volume that gives a luxury European sedan 600 kilometers now delivers over 1,000. Scale the pack modestly, and 1,500 kilometers becomes achievable without adding net mass. You reduce it. The casing is equally radical. CATL replaced aluminum enclosures entirely with aerospace-grade titanium alloy, the same material class used in supersonic aircraft and deep space hardware. Compared to aluminum, the titanium casing is 60% thinner, 30% lighter, and delivers 3 times the tensile and torsional strength. Approximately 400 kilograms of structural dead weight is eliminated from the vehicle floor pan, while resistance to side, impact intrusion and road debris increases substantially. Titanium's thermal properties also solve the heat management problem. Its conductivity characteristics enabled CATL to integrate micro-scale liquid cooling channels in direct contact with individual cells. Not battery modules, not pack sections, but each individual cell. Thermal control becomes surgical and precise, rather than broad and approximate, eliminating hotspots before they develop and enabling aggressive charging rates. That charging architecture, the Shenzhen 3 protocol, operates on an 800-volt foundation, targeting 1,000 volts in next-generation implementations, using fast ion ring technology on the graphite anode surface, a highly porous microstructure, creating a multi-lane ion transport superhighway. The system charges from 10% to 98% in 6 minutes and 27 seconds, less time than it takes to fill a combustion vehicle's tank and walk back to the car. After 3,000 full hypercharging cycles, the pack retains above 90% of its original capacity. Both the range problem and the charging problem are solved in a single integrated architecture. CATL does not sell cars. What they sell is a systematic competitive advantage, and Chinese automakers are deploying it across every segment simultaneously. The Avatar 12, developed through the alliance of Chang'an Automobile, Huawei's digital systems, and CATL's battery technology, takes integration further than any European brand has attempted. Through CTP 3.0 cell, 2-pack architecture, the titanium battery casing becomes the structural floor of the chassis itself. It is not a component inside the car. It is the car. Volumetric efficiency increases by 72%. The battery stiffens torsional rigidity and contributes to suspension geometry stability under dynamic load. BMW and Mercedes still source battery modules as separate supplier components bolted beneath conventional body structures. By CATL and Avatar's standard, that is 2 full generations of integration behind. The Zeekr 001 FR proves the same chemistry scales to performance extremes. Quad motor, 1,265 horsepower, 0 to 100 in 2.0 seconds, from a battery platform architected for 1,500-kilometer range. The Li Auto Mega applies identical technology to a full-size luxury family MPV. eliminating the assumption that large, heavy vehicles are incompatible with serious electric range. One chemistry, every segment. One unified platform advantage that Stuttgart, Munich, and Tokyo cannot currently replicate on any confirmed production timeline. The legacy automakers did not fall behind because of inadequate engineering talent. They fell behind because their leadership chose managed doubt over genuine urgency and comfortable delay over the discomfort of real transformation. The 1,500-kilometer barrier has not simply been crossed. It has been demolished through aerospace metallurgy, biomimetic materials science, and a charging protocol that makes the petrol station feel like a relic of a slower, less precise era. There are no remaining goalposts to move. The last credible objection to battery, electric vehicles for long-distance travel, is no longer a limitation. It is a closed chapter. The only real question now is how long the market will wait for legacy automakers to catch up before it simply moves on without them. Based on everything CATL just demonstrated, not very long. What's your take? Has CATL permanently ended the combustion engine's last argument? Or do the legacy brands still have a move left? Drop it in the comments. And subscribe for the deepest technology breakdowns on the channel.